Hi, good morning, everybody. You should be seeing me, hearing me, and seeing the slides. Yes, okay, great, thank you. All right, let's get going. We're here for today's Rubin Science Assembly, and today we're doing cross-match to user-uploaded tables, and we're going to tell you what that means and show you how to do it. So today's agenda, as always, we're going to start with some announcements. Then we're going to switch over to Gloria, and she's going to give you first a portal tutorial on how to upload a table to the portal and do spatial cross-match. Then the basics of how to do that in a notebook tutorial. And then I'm going to show you again in a different notebook tutorial, the specific case of using user table upload and cross-match when you're trying to get a bunch of light curves all at once. So we got some general cases, some how-tos, and then the specific case of trying to get bulk light curves into your hands. To start with announcements, this year, well, in January of 2026 at the AAS, there's going to be 2 Rubin-related special sessions, both of which are accepting abstracts for contributed talks and or posters until October 6th. So that's Monday is the AAS abstract deadline. One of them is on Rubin First Science results. That one's accepting both talks and posters. And the other one is on Rubin and satellite constellations, and that one is accepting contributed posters. So if you're going to the AAS and you're submitting an abstract, consider whether these 2 special sessions might be good for you. Second announcement is that LSST at LATAM, so that's the LSST at Latin America conference, is December 1 to 5, and it's in Mexico City. I think the abstract deadline has closed, but I don't think the registration deadline has yet. So if that's of interest to you, or if you're geographically located in Latin America, you can consider going to that meeting. Looking forward over the month of October to our upcoming Rubin Science Assemblies. Next week's going to be a drop-in. After that, we'll have a tutorial on astrometry that focuses on the components of the WCS that comes with the images and how to use it. Then later on, we'll go back to a drop-in office hour. And at the end of the month, we'll have a tutorial on stellar science with Data Preview 1. Just a few words about commissioning. As you may have heard, Summit operations are now in a pre-planned shutdown that'll last through October 17 to 20 or so is the plan, as they finish up some final things in the dome that requires the telescope to not be running overnight. If you're interested in seeing how the science validation surveys have been progressing, you can go to this link where survey progress is reported and characterized. It's those science validation surveys that they've been doing over the past couple of months will eventually become Data Preview 2, which will come out next year. You can always follow along with commissioning updates in the Rubin Community Forums news category. The link is here. Keith posts them, has been posting them every week or so. Now that we're in shutdown and things are changing, I think the cadence is going to change for that, but you can go and keep an eye on that kind of news. And then there's just 2 pictures here that I grabbed from the staff Slack that show a pretty sunset and show the summit staff on the last night of operations before the shutdown. One other standard announcement we always make in our Rubin Science Assemblies is to make sure that everybody knows that you have a users committee. They have a website. They are always interested to be contacted by people who are using the Rubin data products, tools or services to hear how it's going. Does it work the way you need to? Do you have ideas for improvements? The users committee is who you want to be talking to about that. They've got an email address and they also have a Google form. Or if you know any of them, you can contact them individually. And they would very much look forward to hearing from you. And another standard announcement, if you are a user of the Link Frameworks tools, they do have an office hour every week. That's right after the Rubin Science Assemblies, so 10 a.m. Pacific, every Thursday except for the Thursday when they're doing their Link Tech Talks. So if you use Link Frameworks or if you're curious about their software, you can drop in there. This is a slide that I want to do before I talk. So we'll come back to that, and I'm going to hand it over to Gloria to get started on some portal stuff.
Okay. Hello. I'm going to put some things in the chat. So I'll be presenting this portal tutorial that I just put in the chat. And it does require, if you want to follow along, it does you would need a table to upload. So I'm just gonna paste. Oh, it's not very copy pastable in the chat. But so if you go to that tutorial and you go to step number 4, there's a table that you can copy and paste and save as a CSV if you do want to like follow along. But you don't have to. You can just also watch. It's a pretty short tutorial. Um, okay, let me share screen. Okay, and I am sharing the Urban Science platform.
Yes, I see the landing page for the RSP.
All right. And if you want to go to the Rubin Science platform, that's at data.lsst.cloud. But if you've never been to the science platform, when you land, there's different aspects that you can interact with. We're gonna start with the portal. And when you first go into the portal, there's different tabs here. You have a results. You can interact with images, catalogs, and you can just also directly upload tables. But for this particular tutorial, we're gonna try to do a spatial crossmatch with a table that, as you can see in the chat, I'm gonna upload a table that has some array index. So for that, you can go to the DP1 catalogs. And when you go to DP1 catalogs, you see that there are different table collections. Default is DP1, which is what we're going to be using. And there's different tables that you can select. For this particular tutorial, we can just leave it as the object table. And you'll see here all of the different columns from the table that's selected here. There's like 39 columns that are selected by default. For this, I'm just going to leave those columns selected. And you'll see that some of the columns are coordinates, and those are the chord deck and chord array. And on the left here, you can see that you can enter some constraints. So you could do like a spatial query, temporal query, or like you can search by object ID. For this particular presentation, we can just leave the temporal and object ID unchecked. So we're going to do a spatial query. And you can do a single object, you can just input the coordinates of your favorite object here. But you can also do multi-object, which is what we're going to try to do. And when you click on that, there'll be a little pop-up window. And this is where you can upload your table. And I'm going to pause for a second here just in case you did want to grab that little CSV copy paste and upload a table here. But just briefly. Okay. So very simple here. You can just click on choose file, and it'll take you to, your own computer. And here I have saved the table already as DP1 106 one user table, and it's a CSV. And once you select your file, it should show you here the columns are in your file. Here I have just some like a identifier for each object, and then an array and deck, and it should tell you also what the type of each column is. But yeah, so then you can just click on the table, and I believe if you go to the results, it should show you the table here. Okay, yeah. So if you click on results, it should show you the table that you just uploaded. So here's just the coordinates for 5 different objects from the SDSS. But going back to the DP1 catalogs, so it should have automatically detected that your position columns were REN deck. If it has REN deck in the name, it should figure it out. But if it didn't, you can click on position columns, and you can tell it what columns to use for your cross matching. And then in the second, where it says from the selected table on the right, it should also automatically detect that it's a chord array and chord deck from the object table. But yeah, and you can select the crossmatch radius here. For this, we're going to use a radius of 1 arcsecond, and you can just leave the default row limit since it's just 5 objects, so it should return at most 5. Well, actually, no, but for this, it will return just fine. Yeah, okay. So here I'll just click on search, and it does take just some time with the uploaded tables. It is a bit slower than if you were doing one single coordinate, but okay. And hopefully other people's, if you're actually running the query, hopefully it finished. It automatically went to the results table. And here you'll see still the tab for the uploaded table, but now there's another little tab that shows you the results of the cross match. Here it found five matching objects from the object table. And you can see here the different object IDs for those objects. And actually, if you go all the way to the end, it also has the ARIAN deck that was used to match. And here, it's still loading, but there will be some data from the four source table as well. So if you click on each one, it'll look different. Uh, yeah, and on the right here, there should be uh, the deck versus RA from the object table. So you can see the positions of the points that we matched. And if you click on coverage, there's also, you can see, where in the images the positions are. But yeah, so that's pretty much it. I don't know if anybody has any questions about this. It's a pretty easy process, I hope. Okay. I will then go to the notebook aspect of the RSP, and we'll present a little notebook version of that. Oh, yep. Tim?
Yep, sorry, just trying to find the buttons. Question for you. Do you have a sort of sense of how long the cross match takes scaling with size of uploaded catalog?
Um, I don't have like a quantitative answer. In my
Yes, I do.
Oh, yep. Did someone say something? Okay. Uh, Not in the portal, but in the notebook, I did find that there was just some amount of time that it took just for the fact that I was uploading a table at all. I didn't find a difference between like a few objects versus like around 10,000. It was still like at least in the notebook it was a couple minutes. Um, but I don't have something more specific than that.
Okay, thanks.
Melissa, I don't know if you do. No, okay. All right. Thank you for your question. Okay. So if you go back to data.lsst.cloud, and you have to click on the notebook aspect. And I already was using the notebook aspect, but if you hadn't already, it should allow you to select a image. So if you just leave it default, the recommended, and then the default container size of large. But once you do that, it might take a second to actually load. Um, but you'll see here that there is at the top a tutorials tab. And there you can find all of the tutorials that we've created for all of the different data previews here. But for today, we're going to use data preview 1 and how to use the RSP tools. So there's different categories of tutorials. The most basic ones are how to use the RSP tools that really show you, how to use the tools, and then a little more advanced data products that go into the different catalogs and images, and then there's some science demonstrations. But for today, we're gonna do the catalog access, the series 102, and then 102_6 cross-match to upload a table. And I've already opened this before, so it will ask me if I want to overwrite it, and I do. And that should give you like a fresh version of the notebook if you've used it before and you've made some edits or something. But yeah, so this tutorial, the objective is to use the tab service to cross-match to upload a table. And I'll show how to do that with a couple different use cases. So first, we start by importing all of the packages. We're gonna use AstroPy table just to load a table. And then PyVO, I'm not sure if that's how you actually say it, but that's how I'm gonna say it. PyVO to query an external database, and then from the RSP tools, get tab service to actually query the DP1 data. But yeah, so you can, if you haven't used the Jupyter Notebook before, to execute it, you just do like Shift Enter, or you can go to run here, and I think you can just do run a selected cell. But yeah, so the first thing we do is import some packages, and then we create an instance of the tab service. And then, so the first example will be loading a table that we have stored. And this is from the SDSS Sky server, and it's like anything in that database within half a degree of the center of one of the DP1 fields. Here, the low ecliptic latitude field, and those are just the coordinates here. But you don't have to actually upload this. We have stored it here for you, and we're gonna save it as UT1. That's just user table number 1, and loading it using AstroPy. And this is again a CSV file. And then we can just look at the data. Okay. So in this case, we have almost like 9,000 objects, and you can see their object IDs, their array and deck, and then this also just has some magnitudes. But we're gonna attempt to cross-match all of these objects to the object table from DP1. And the first thing that you do is write your query. So we have a lot of tutorials that show you how to write a tab query, and we use ADQL for this. But first, we're just selecting the tables from the table that we're going to upload UT1. So we're getting the object IDs, the array and deck. But if you wanted to, for example, compare, the magnitudes from that table to the ones that you get from the object table, you should also, grab those columns. But yeah, and then from the object table, we're just grabbing object ID, coordinates, and then the C model magnitudes and all of the 6 LSST bands. And now the part that might be new is this part where you're grabbing things from the object table, but then you're joining it with the tab uploaded table here. So you do tab upload and then a period and then the name of your table here, UT1. And we're saving that as UT1. And then this is just, your spatial constraint of like matching to within 1 arcsecond. Now, the other new thing is, so the next thing is to run your query. So the new thing here is not only to pass the query, but you have to specify the table that you're uploading. So here you would do uploads equals the name of the table and the actual table. And like I said, it does take maybe like a couple minutes. So I guess this might be a good time for questions if you have any.
Gloria, could you go full screen on your um, page?
Yeah, was it?
And maybe get rid of the table of contents on the side. That just make it bigger.
Oh, yeah, let me zoom in too.
Thank you.
Okay, yeah. Okay. Did anyone's query finish? This has passed the usual amount of time this takes, but
Yeah, when we're all doing the exact same thing,
yeah.
usually. Yeah.
Yeah. Okay, maybe think I can execute this one. Oh, my query completed. Okay. Yay. Okay, so the last thing was just to display the results. And this just shows you in the order that I selected the columns. Here I just selected all of the object ID array index from the uploaded table. And then starting with the object ID, everything else is just from the from the object table. And you'll notice that not all of the things that we uploaded had a match, but it's still like that, you know, it did give back a lot of results. But yeah, so that was that demonstration of just like having you have saved some table with some coordinates and you want to cross match using coordinates to the object table. And then you can just delete all that stuff. But the next use case here is matching using some type of identifier, and also to upload a table by that you got from an external query. So for this, we're going to look for solar system objects from Gaia and use the minor planet catalog designation to match it to the MPC orb table, which is part of the solar system data products. And we're gonna query the Gaia database using PyVO. So the first thing that you need to do is to, I guess, define how to access that the Gaia tab service. So we have given you this URL, and you'll notice that this is a slightly different way of it's doing an instance of tab here. But yeah, so, and then here you just give it that little URL that you define. And we're going to query the solar system object orbits table, which we're going to look for main belt asteroids. And for that, we're using this definition from the JPL Horizon Small Body Database, which says that this can be the main belt asteroids are between some major axis of 2 and 3.25 AU, and then Q greater than 1.66 AU. But here from that table, we're going to query for denomination, which is, I think, what they call the where they store the MPC designation. We're grabbing some major axis and some other orbital parameters. And just looking for things that have more than 200 observations. And then just running the query using that. Okay. And upon looking at the table from Gaia, you'll see that the denomination has this specific formatting. So the MPC orb table uses the standard MPC designation, which does not have an underscore, and this part of the name is in upper caps. But yeah, so one thing that if you're uploading your tables, you should check to make sure that the format of your table either matches the table that you're trying to cross-match to, and also there's some things that are not supported. So the first thing that we're going to do is to reformat this table. And we're going to get rid of the underscore, and we're going to make it into an upper strip. And then the other thing is, did I do something? Okay. So then you may have noticed that we saved this as a pandas table. But we can convert it back to an AstroPy table. The reason I say it as a pandas table is because it makes it just very easy to like convert. But you can convert it back to a AstroPy table. And then you'll notice that some of the columns have data type Unicode, and that is not supported. So you can convert them from Unicode to byte string. But now that your table is formatted, we can just do the actual the cross-matching query. And for here, similarly, we're just grabbing some columns from the user uploaded table. In this instance, we save it as user uploaded table 2. We're grabbing the column that we called MPC designation, and the MPC designation from the MPC orb table. And we're grabbing that table and joining it using the tab upload here, where the two designations are the same. And so the point of this query was to search the MPC orb table for the solar system object ID, which will then allow you to go into the other solar system table and grab data just for those specific objects that you're interested in. But yeah, we can just run that query, and this one it takes like a minute as well. And now lastly, you can just look at your results. And this found solar system object IDs for about 800 of the 1,000 main belt asteroids. Yeah. So that was all. I don't know if anyone has any questions before we go to Melissa. Okay, I'll stop sharing.
All right, thanks, Gloria. And we always have the chat for questions. Yeah, while I'm talking, if something comes up. Yeah, just use the chat. All right, I'm gonna switch back to slides. And just go on to this question, like a special case of when you need to do user upload table cross matches. The specific question, does LSSD have a light curve at this location? This is something that we've seen a lot of queries, a lot of users running queries that they're clearly trying to answer this question, but they're not always doing it the most efficient way. And so the notebook that I will show provides the guidance and the best practice for trying to answer this question. So making an efficient query to find out, does LSSD have a light curve? Did they detect anything in the time domain at this particular location? Requires understanding the tables. So just as a reminder, there's the object table, that is the detections in the deep coat images. And in the object table, it's one row per unique coordinate. Associated with the object table is this forced source table, and that contains force photometry for all visits and all difference images. So that's all the science images, like direct images and all difference images at the location of all the DIA objects. So in the force source table, there's multiple rows that actually have the same coordinates. Because it's one coordinate from the object table, and then it's the force photometry in every single visit and difference image. Reminder also that there's the DIA object table, and that is detections, it's made up of detections in the difference images that are all associated by sky location, so at a single coordinate. So again, with the DIA object table, it's one row per unique coordinate on the sky. Its associated table is the forced source on DIA object table, and that has the force photometry in all the visit images and all the difference images for that location of a known time varying object for a known DIA object. So again, in the force source on DIA object table, it's multiple rows per unique coordinate. So on the left, these are like the static sky versions of the tables, and then at the right, it's the time domain versions of the tables that have the light curves at the known locations. It is not great to make spatial queries on the force source tables because they have multiple rows per coordinate. It's quite inefficient. So that's not the way to go about asking if LSST, has a light curve. Don't ask over and over on the force source table. But you do want to make spatial queries on the object and DI object tables. So the notebook we're about to do demonstrates how to do this. You make your spatial query on object and DI object, and then you link them and you pull the light curve out of the force source table for a given object. The other pitfall we see people running into is putting tap queries into for loops. This isn't forbidden, it's just a little dangerous and not the best way to go about things. So I think when you have a list of RA and DEC and you want to know, did LSST detect something here? Is there a light curve at this location? It can be pretty tempting to do a for loop over a bunch of tap queries that might look something like, for this coordinate in my set of coordinates, define my tap query to go and look at the table and see if there's anything there, submit the query and get the results, and then do this over and over for every location. You're not forbidden, it's just not, it's really not the best way to go about it. It's better to use the tap functionality for table upload and cross-match that Gloria just showed you. So it's both notebooks 102.6 and 306.3 that we're about to do, demonstrate how to do this. So those are the warnings. Those are some of the things we've seen people do, which it makes sense that you would try to do it this way, but we want to show you the better ways. So we come back into the notebook aspect here. Let's, in DP1, this time we're going into the 300 level because this is a fairly science-specific demo about how to get light curves in particular. And this notebook that I'm about to show lives in the 306 series on extragalactic transients. and it's showing you how to do cross-match. It's called cross-match queries, and it's sort of the specific case for getting light curves. So you should be able to navigate to that and open this 306.3 notebook. The introduction basically just says the same things I just told you in the slides about what to avoid and what to do when you're asking the question, did LSST detect something at this location? As usual, we start by importing a bunch of packages, defining the tap service. And since at the end of this notebook, we plot some light curves, we want to use the standard filter colors that are designed to be colorblind friendly, yet still represent each of the 6 LSST filters. So we define those here so that we can plot our light curves. This particular example, when it asks, is there a light curve that in LSST at this location? What we've done is sort of make this sort of a fake table of RA index that are in the ECDFS field. So I'm just going to define the center coordinates of the ECDFS field so we can put it in our plot later. And then we have this sort of synthetic user table. It's a very contrived situation, how we've made it. We took known DIA objects that definitely have a light curve. I already know that they do. Took a bunch of objects in a certain area, just a bunch of random stars, and then a bunch of random coordinates. And in this file, which let's upload it and just show it, I've just given them a name that's in the 100s. If it was a known DI object, it's in the 200s, which you can't see because the table's truncated. If it was a known object, and then I got a name in the 300s if it was random. Basically, we just wanted to give a table for this demo that includes some things that will definitely have a light curve because they're already DI objects, so we know they're going to match, and some things that won't because they're just a random sky coordinate. So this file is just giving you a bunch of coordinates, some of which will match, some of which won't, just to be like a realistic experience. This cell just makes a little plot in RA and DEC to show you what this fake little table contains. So it's a bunch of objects. They're all around the same location, about equal numbers of known DIA objects, stars that may or may not be variable, and just random sky coordinates. So this is our starting place. You would use your own table here if you were doing this for real for science. And then the rest of the notebook shows sort of 2 ways to do the query of is there a light curve at this location. Section 3 shows how to do the query in 2 steps, kind of like a very pedagogical way of how to go about making this query. And then section 4 is going to combine the 2 steps into one single table join. So we're kind of doing the same thing twice. It's just in section 3, we do it kind of the easy way. And then in section 4, it's a little more complicated, a little bit more advanced use of TAP. So let's start with the query in 2 steps. This is going to be very similar, I think, to what existed in the tutorial that Gloria showed you. We have our user table. And if you skip down actually to the second cell where we send the job to the TAP query, you can see we're defining this user table as having the name UT when we submit it to the TAP service at the same time as we submit our query. So we submit our query statement and our user table defined as UT at the same time to the TAP service. And in this query, we are selecting various columns from GIA object, which is the table we're trying to match to, and then our name and our RA index from the user catalog. That is our list of RA index. We're also going to here ask the TAP service to give us the distance. So not only are we doing a cross matching, but for the ones that do get matches, we're going to ask it for the on-sky distance to come back. So we know the distance between the coordinate we gave it and the coordinate that it matched, and the object that it matched to. In our case, because we made this synthetic little table that had a bunch of known DI objects that we know are going to match, all of these distances they're gonna come back as 0. So everything that gets a match is a known object that we pulled the coordinates out of the DI object table in the first place. So the distances will just be 0 because they're perfect matches because of how we set this up. But you would want to know the distance if you were doing a for real cross match to your own catalog. This is the part where we join the DI object table to our user uploaded table, and we set the cross match to be, in this case, 0.5 arc seconds. And we make one more constraint on our query here, which says we only want to cross match to DI objects that were detected at least 10 times. This is demonstrating how you can write a little bit more complicated of a query and put additional constraints on the goodness of the objects that get cross-matched with, or if you know you don't care if there's a light curve that was detected only once because you can't use that for your science, so you want to put some constraint and be like, give me every light curve that LSST has that at least has a bunch of detections that I can actually work with. So that's what this example is doing in terms of cross-matching to DI objects. So we set up our query and then submit the query along with our user table at the same time as an asynchronous query, and we let it run. And this is the time where we pause for questions while this runs its way through. Right. That completed. So we fetch our results. Great. And we can display them. So in this case, with this synthetic user uploaded table that had some DI objects, the things that we already knew were detected by LSST are the ones that end up in the output table and had successful cross matches. So this is as expected. But of course, when you use a real table of externally defined coordinates, you would have some that match and some that don't. So in this case, we get 13 matches back. Wonderful. This cell just does a little thing to make sure that we didn't match with multiple DI objects. Since we used a radius of cross-matching of only 0.5 arc seconds, I did not expect that any would be doubly matched with more than one DI object. There won't be more than one DI object within 0.5 arc seconds. But if you had used, for some reason, a larger cross-matching, you do want to double check to make sure, see how many double matches you might have got if you're using a larger radius for cross-matching. So do be aware of that. LSST is going to go so faint that there will be lots of things along any given line of sight. So now that we have cross-matched and we have 13 of our RA index have corresponding matches and have a DI object ID from the DI object catalog, we can now go to the force source on DI object catalog and retrieve the light curve for each of these matches by the unique object identifier that is here. So that's what the 2 steps are. Step 1 is a cross match to DI object, and you get the DI object IDs for all your cross matches. And then step 2, you go to the force source on DI object table, and you say for each of my objects that I know have force photometry, you just grab it. So this second step, you're not really like asking the force source table, do you have a force source here? You already know it does because the object has a DI object ID. So it makes it a much more efficient query when you're just retrieving something that you already know is there. And you have the DI object ID for it. It's a better way to retrieve your force photometry. So the first thing that you do is you set up just a string list of all of your unique identifiers, all of your DI object IDs. And then when you write your query on the force source on DI object table, where you want to pull out, for example, the band and the difference flux, in this case, we're getting difference image flux light curves. You're going to get those from force source on DI object only where the DI object ID for every force source is in this list. So it's going through, each of your DI object IDs and basically getting the light curve. There's an extra join that you have to do here because the force source on DI object table doesn't, it has the visit identifier number, but it does not have the actual Julian date of the detection. So you have to do one more join to the visit table, and that's where you're getting the midpoint MJD. So that's basically, it's just the modified Julian date to go with, which you need if you want to plot a light curve. You want to plot flux versus time. So you have to do one more join to get time based on visit. So that's how this query is set up. It's going to the force source on DI object table, and it's getting all of the force photometry for each of your matches. And so we let that run. And that's nice and quick. Yes, the job was completed. And in this case, about 7,000 individual light curve points for your 13 DI objects, which, makes sense. There's a measurement in every single visit, in every single difference image associated with every visit. You can take a look at that table that you returned. You've got your flux and you've got your MJD and you've got your band, and that's what you need to make your light curve. So there it is, coming out of that sequence of steps, of 2 steps. So that's great. We can get rid of those. And then the query in 1 step. So this one does a bunch of joins all at once to basically do those 2 tap queries all at once. So you can see here, you're starting with the DIA object catalog, just like we did before. You're joining it to your user uploaded table, just like we did before. Your main constraint is, again, that cross match between the DI object table and your user table within 0.5 degrees. So that's still happening. And then at the same time, you're also joining to the force source on DI object table based on DI object ID. And again, that one extra join to the visit table so that you can get the MJD out. So this is doing the same thing as the 2 steps we're doing before. It's just doing it all at once. So you can see in our select statement, we're actually selecting columns from 4 different tables, from the DI object table, from the user table that you've uploaded, from the force source table, getting the same things, the band, the difference flux, and from the visit table. That's where that MJD is coming from. And on top of it all, we've got that constraint that we put on the number of detections, to return just light curves that have a lot of detections. So it's doing the same thing as section 3. It's just doing it all at once. So we can again submit that job. So here it's still only doing the cross match with DIA objects, which is the table that has 1 row per coordinate. And then it's going to the force source table to grab the light curve every time there's a match. Interesting. Oh, error. What happened? Oh, timeout. Timeouts are kind of rare, but they do happen either during the query phase or sometimes during when you're fetching results. It is the internet. Timeouts do happen, connection issues happen. It's another reason why it's better not to put queries into for loops because it can be hard to tell then if it does fail eventually, why it failed. Did you give it a bad query in one of the iterations of the for loop, or was it just a connection error? And then if you've been, doing things in your for loop, you've kind of lost it all if they get a connection error on your 100th submission of a tap query. Okay, no connection error this time. It's all happy. Again, about 7,000. It's the exact same results that we got from the 2 steps. It's just doing it in a more advanced way. And then just to wrap things up, because we retrieved some light curves, we might as well plot them. All this is doing is sorting by DI object ID so that this particular tutorial notebook always plots the same six light curves. So this is just a bit of a quick look. These maybe aren't the most interesting ones in the world, but this tutorial isn't actually about time domain analysis or anything. It's just about using the tap service, and it definitely did that, and we got light curves out. Yes, the times. Thank you, Tim. Yep. I have a outstanding ticket still to go through and like do some more documentation on the types of times that we have. And there you have it. So that is your advice on how to get light curves out of the LSST tables. We are very happy to take any questions that you might have. You can use the raise hand, or you can just ask in the chat. I'm going to stop recording.